Hello, this is homework set 1 of tutorial, this is problem 1 of tutorial 1. This is probably the first video that you're seeing, although it's not the first video that I recorded. I recorded another video first because I thought this problem was quite intimidating, but it's not. It's really not. This is a little public service announcement. I am a first year TA. Hopefully I'm not getting in over my head by making these videos and realizing like in 6 weeks time that I have far too much on my plate, but hopefully you guys will benefit from this. This is all for your benefit after all. That'll make things a little bit more clear. Anyway, to problem set 1. I said I thought this was intimidating, but it's not. It's really not. There's just a few a few things you need to keep in mind when you're doing this, and as long as you keep track of everything, you should be okay. This is your problem, and it's asking you to find the magnitudes, directions, locations of the maximum bending stresses, shear stresses, and torsion stresses. Okay, so first things first, I don't know how much of this you guys will have trouble with. I'll just let you know that you need to use these 3 equations. You're going to calculate the moment, torsion, and shear, and once you have those, you're going to use these equations to turn those forces and moments into stresses. Now, to do that, to calculate those forces, let's look at your problem. You have something that looks essentially like this, right? Where you have P acting here. Okay, now remember that you can move forces around as much as you want, as long as you remember to include moments. So for example, this force here, you can move this to the center, as long as you add a moment that's equivalent. And recall that this is d over 2. As long as if you just move it like that, as long as you add that moment, that's fine. So what you want to do before you do anything else is you want to transfer everything down to the base. So for example, this moment, let's draw a coordinate system. This is x, this is y, and this, we'll call this x, y, and z. In that case, recall that this moment is going to be mz, because it's about the z-axis. If we bring everything down to the circle, to the base, we're going to have a series of stresses. If we bring P down from up here all the way down here, we're going to have P acting here. In order to make it equivalent, we're going to have a moment that goes like this. Moment is equal to 0.75 LP. And I already said we have this rotational moment, which is here. Okay, once you transfer everything down, keep in mind that these are not reactions. These are forces that you're exerting on the structure. They're external forces. Your reactions, consider this base to be fixed, and what you have are 6 reactions. And technically, I've already given you what these 6 are, but I'm going to let you solve them for yourself. I will tell you that you have no forces acting in the y, and no forces acting in the z, and you have no moments about the x-axis. An important thing to note is that your sign convention, you can use whatever sign convention that you want. I personally always use the right-hand rule for my moments. So for example, my mx, I say this is my axis, and this is the direction of my moment. So my moments, if I had them like this, I would define this as mx positive, this is my positive, and this is mz positive. Now remember that your forces always act in a direction opposite to your reactions always act opposite to your forces. So to keep this thing from sliding this way due to this force P, you need to have a reaction that's going to negative P. Okay. Now this is just to calculate your reactions, to calculate your moments. When you're actually doing your shear, in this, for example, in here, your shear, you can imagine this if you want. It's like a beam going up, or it's just a column basically. But you have this force here. Just remember that your shear is going to be like if you have a beam, if you have like a cantilever beam that's like this, and you have a force here. What is the shear that develops? The shear is just going to be here, right? That's all your shear. So your shear is going to be very similar to this. Okay. Keep in mind that your formulas call for two different kinds of moments. This moment, sigma is your normal stresses. So this is your stress due to bending. So what causes bending? Because you know you have two moments here, so you need to use the moment that causes bending. In this case, the moment that causes bending is the moment that acts upon the longest length. I don't think I'm explaining this correctly, but I don't know if you agree with me or not, but this thing is much taller than its diameter. Let's assume that it's taller than its diameter. Because of that, my will become your bending moment. The other torsion, the other moment you use torsion, this T will be the moment due to twisting, the twisting moment, the moment that causes twisting in your structure. And in this case, this will be mz. And I think you can agree with me here that in this case you're twisting it. Uh-oh, that was bad. Yes, you're twisting it. Okay, enough about that. The only thing that I think might cause trouble here is Q. I don't know if I'm remaking this video after having office hours today, because I realized it wasn't very clear how I explained Q. But if the Q I'm referring to is this equals VQ over IT. This is your shear stress due to shear, your actual shear stress due to shear. This is your shear stress due to torsion. When you're calculating Q, you probably all seen this example of the I-beam, and you probably remember seeing something that looks like this. And where your maximum shear stress occurred in the through the centroid, I believe, is the term. This was for shear that was acting this way. And when shear is going this direction, you have zero shear at the top, zero shear at the bottom, and you have your maximum shear in the center. When you have a sorry, before I go on, when you're trying to calculate the shear, you choose a point. Let's say that we're interested in this point. You choose a point. Once you choose a point, you go from the top, the point closest to the origin of the shear, and you go down until you draw an imaginary line that's perpendicular to the direction of your shear and goes through the point you're interested in. And this will become the area for your Q. Recall that Q equals A y bar, where A is the area above the point you're interested in, and y bar is the distance from the center to the center of A. Not the distance from here to A. From here to the point you're interested in, but the point from the center to the center of the area you're interested in. This will become more important for problem 3. I'm just introducing this here. When you're doing a circular member, you have this. In our case, our shear is going to be directed this way. Let's assume it's directed this way. We have to draw this diagram on its side. We end up with the diagram that's like this. And your maximum shear stresses occur here. Now, we're interested in the maximum the maximum shear stresses. So we're actually interested in points, these 2 points. How do you get Q for here? Well, you start, this is the direction of the shear. It starts, this is the origin of the shear, I guess you can say. And you take this area. You need to use the Y bar for this area, so the distance from here to here. And that is given to you in your equation sheet. Here, Y bar. So that is Q. In our case, T, because we're at the maximum, you're just going to use the diameter. The diameter will be your T. I is in the formula sheet as well. So you just need to use this equation for I. Once you do all that, I believe you should be set. Remember that you need to find bending stress, shear stress, and torsion stress separately. So you're going to find sigma, you're going to find tau torsion, you're going to find tau shear. Okay, that is all part A. Oh, I'm just looking at the camera now and I realize I hope I kept everything in frame. Okay.